Good morning, everyone. I am Eleonora from Italy, from the University of Bologna. And this is my talk. And I want to acknowledge the project for which I'm here, which is called Fedora. Fedora is a project, European Horizon 2020 project, which is basically on I will cover some of the issues we are dealing with in the project. And especially it is focused on the so-called future-oriented science education, which is at the frontier now of research in science education. I will deal with it in the presentation. So, the premise. Okay. Great. Thank you. So the premise from which we have to start when we talk and introduce future-oriented science education is that we live in a society, in the society of acceleration, as the sociologists say. I mean, we have talked about it a lot in these days, and it's not only a matter of change. Our society is not only changing, but what is changing is the pace of change itself, so the acceleration, basically. And in this context of profound uncertainty, what really suffers is also our relationship with the future, that becomes problematic and source of anxiety. So instead of a promise, future starts to be seen as a threat. And this is far more true with young people, especially those who are starting to feel marginalized or excluded, and who are struggling with the idea that school is not providing them something meaningful and something that they can perceive as useful also for their position within the world of work. So they are basically struggling a lot, and many reports, international reports, are saying this, in projecting themselves into the future, and so and also in seeing themselves as agents in the present with an orientation toward the future. So this is where future-oriented science education basically starts. And why science education? Because this field, which is very recent, aims at reconstructing the conceptual, epistemological, and methodological structure of science to support students, learners, in recognizing how the present is complex, but via an explicit reflection on the future, explicitly focusing on the future. And we do this by focusing on the nature of science, on the epistemological layers of science and of disciplines. I'm a physicist, but my colleagues are computer scientists, mathematicians, and we are doing it starting from the disciplines. It is necessarily an interdisciplinary field that embeds a lot of perspectives, from the learning sciences to the sciences and STEM disciplines, to also humanities and sociology. And this is a metaphor that became for us in the project, and for me specifically in my research field. This is a metaphor of the future cone, the cone of the future, which comes from the disciplines of futures studies, which contains a plurality also in the name itself. The idea is that we cannot think at time and at future as a sort of line. We start in primary school at seeing history as something linear. We have the past that causes basically the present that will cause the future, and now we have a sort of more expanded way to think about the future in this metaphor of a cone, in which different kinds of futures can be identified as the probable ones, like the closest to the line, the horizontal lines, but then we have also plausible and possible future, which contains all the possibilities, And it's not only a matter of probability, the idea of projecting ourselves into the future. It's also a matter of values and of desires, because the future studies also identify a particular type of future, which is the desirable future, the preferable future, which contains not only projections into the idea of what is more or less probable to happen, but an idea of what I would like to be realized. And why complex systems? Complex systems, really, if we read the literature, as I have studied a lot, the literature in future studies, complex systems is an everywhere metaphor for describing this change in thinking about the future. Because in complex systems, one of the ways to think about complex systems is from an epistemological perspective with enormous change in terms of causality. We pass from an idea of determinism, which is usually conveyed also by disciplinary learning. Let's think about physics. We have the laws of motions that are basically grounded on the idea that knowing the present, we will be certain about the future evolution of a system whenever we will look at the system itself. And we pass to another kind of causation that is far more complex and includes, for example, the so-called butterfly effect, so a nice sensitivity to initial conditions of the system, feedbacks, effects, and also emergent properties, on which, we really challenge our understanding of how causality needs to be understood. So our stance is that exploring non-Newtonian, non-mechanistic, non-reductionistic, non-deterministic scientific models can help the students to envision the future in a more open way, to open the cone, to open the line, and following the metaphor before. And actually, complex systems and futures are really are becoming more important also from a political point of view. I don't know if you know this, but in the European Union and in Europe in general, this is becoming like a trend. This is the Dream Comp, the competence framework elaborated by the Joint Research Center of European Union, that for the first time embed future thinking and system thinking as important competency to tackle with the sustainability challenges. So, this was in some way also a product of the Fedora project, because authors were involved in the project and in the writing of this framework, but it's becoming something very good. And I come to the third, which is part of the title of my presentation, which are future scaffolding skills. We are studying the effect of our teaching proposals on students, mainly high school students, on their way of imagining and tackling with future challenges and with the very same idea of the future. And we've found two types of skills that can be fostered. Structural skills are those skills that allow to organize knowledge, and in particular organize pieces of knowledge into a systemic view. We are calling structural skills because they build basically the scaffolding of the scaffolding on which the students need also to move through the different levels of the scaffolding. And we come to dynamical skills that are abilities to navigate across this complexity of knowledge, across this scaffolding in a very complex and way to make sense of knowledge. This is a list of skills. Of course, I can provide you more references and we can talk about this, but some examples. In structural skills, we see skills that involve, for example, the distinguish between some details and the overall picture of the system, to unpack an issue into simple parts, to recognize causal and logical relationships within a complex issue. And in dynamical skills, we have skills that include the ability to move, for example, from locally, globally, thinking locally and thinking globally, thinking at the present and thinking at the future and vice versa, thinking at the individuals and thinking at society, also creative thinking, and approach that balance opposite needs, for example. And it comes to this question, how to teach and learn about complex systems. I'm not here to answer this question. We have seen a lot in these days, but what I can tell you is how I teach complex systems, which is with agent-based simulations. Agent-based simulations, I've taken an example here. Is a famous example in Etlogo. Water model, basically you have agents with opinion green or blue, and they are influenced by their neighbors. So they vote as the majority of their neighbors, and we observe that starting, for example, from mixed population, we arrive to clusters, basically, and regions of similar votes. And why I chose this example? Because I can show very explicitly that these local interactions among individuals produce changes at the emergent and the global, global and macroscopic level. So I chose computational simulations and agent-based simulations because of this idea that they allow to see an evolution, so a time evolution, but they also focus very much on the individual level and the individual role, the role of the individual. So let's go inside the classroom and see what happens. I've designed a module on agent-based simulations. It was an 18-hour module for high school students who participated in a university orientation program. It was not mandatory for them. They decided to enroll in this program. The program basically was included the introduction to the topic of simulations, to see how they are research tools, and we included also lectures on agent-based simulation. But the final activity that we made them do, that we asked them to do, was the so-called future-oriented activity, which is common to many activities we are doing these years, that asks in group the students to identify a problem which is relevant for them in the present, a societal problem, for example. It can be related to the school, to the environment, to politics. And then we ask them to choose a simulation to explore different futures with this simulation. Of course, this implied a modelization process, because the simulations that they could experience were very, very, very simple. So they had to, downscale their big problem to the features of simulations. Then to imagine a desirable scenario, to put their values on the problem, and to proceed with identifying the actions in the present and throughout time that could have led to that desirable scenario. My research questions are two. First, future scaffolding skills can be developed. Students can develop future scaffolding skills through this future-oriented activity, and how? And then, are the students able to verbalize the competencies that they have acquired and that they have put into action? After this, I have not said it, but at the end of this activity, we ask the students to present, basically, their results and their story of success, we called it, and we interview them at the end to see, on one side, if the competencies were exhibited, put into action, and then the competencies could be verbalized by the student. These are the skills exhibited for groups. In orange, you see the structural skills to construct the scaffolding, and in blue, the dynamical ones. We see that I mean, competencies can be developed, but we observe that in most groups, all but the sixth one, the structural skills are more frequent than the dynamical ones. So constructing, building the scaffolding is easier or more explicitly present than moving across the levels of the scaffolding. This is a good news because it was very, very different than in other studies in which simulations were not used to build the future scenarios and to explore and to model the problem, the issue. And we have an hypothesis for this success because using simulations allowed students, we think, that allowed students both to handle and dive into the complexity of the problem. Handling meaning structuring their analysis of the problem, to identify the issues, to identify the agents, to identify and unpack a complex issue and reduce it into through a modelization process, to find agents and modes of interaction that could allow the computation. But at the same time, simulations, for their own nature, include a sort of balancing between opposite trends that are included also in dynamical skills, like focusing at the individual and focusing at the whole emergent global picture of the system. And the emergent picture of the system feedback onto the elementary agents. So these tensions that are included in the dynamical skill, individual, society, also present and future, also are embedded in the very same epistemological structure of simulation. So these are our hypotheses for the success. But when we come to the skills verbalized in the interview, when students are asked, I mean, what did you learn? What competencies did you learn through this module? What competencies did you put into play, for example? We see that on average, structural skills disappear. And we have many more dynamical skills, which is an opposite trend than the skills exhibited during the students' presentation. And if we unpack not only structural and dynamical, but we see the list of all structural and dynamical skills, we see that something is very common between skills exhibited and verbalized. We see, for example, this idea that students recognize that simulations and future-oriented activities allow them to recognize multiple aspects of a problem and relationship they could have not been able to see it without this activity, only thinking in general about the problem. And they realize that multiple possibilities can be envisioned, that this plurality of the future was very important for them. But we also observe a misalignment. For example, students in their presentation really put into play these competencies about recognizing the causal structure of a problem. Causes, objectives, results, complexity also of the causes, but then they are not, they seem not to be conscious, aware of these competences they put into play. And at the same time, for example, they recognize the very high importance of interdisciplinarity and multidisciplinarity way of thinking at the problem that it seems not to be like that in the presentation themselves. So we observed a gap between the skills put into play during the group activity and those perceived and verbalized during the interviews. And on one side, as I said, it was encouraging, this result, because in other experiences, students struggled a lot to develop structural skills and skills of constructing the scaffolding. It was easier for them to construct ways to move from present to the future, to local to global, but the structure of the system was hard for them to be achieved. And in this experience, it was not. But when we ask the students to verbalize these competence, things change. They seem to lack words to describe the achievement mainly of structural skills, even if they put into play during the group. So in conclusion, I think to conclude that we have to study more, to investigate more about the topic. We have started to do that using also different data collection tools. But for sure, this misalignment between what you are able to do and what you recognize to be able to do is something that is important to investigate, because literature tells us that metacognition is important. You have to understand what you know and how you learn. And so being this competence of self-perception as said, a cornerstone of social and emotional development, we need to, in research, to investigate ways to make students even more active protagonists of their own learning, also identifying which gain they can have from this specific future-oriented literature. Here are some references, but I'm happy to provide you. And
yeah, so I think we're going to do the other two presentations and we'll have a discussion. That was amazing. Thank you so much. So our next presenter is Susan Yoon from the University of Pennsylvania, and the title is Designing Complex Systems Curricula for High School Science, Agent-Based Models, Practices, and Evaluation of Complex Socio-Scientific Issues.
Yeah, really long title. I'm sorry. Good morning, everyone. So I'm Susan Yoon. I am, oops. Let's see how that works.
Is it working?
I don't know. There's a thing up here that's showing. Oh, I don't know. Yeah. Anyway, I am originally Canadian. In fact, I grew up 3 miles down the road that way, and my mom lives 4 miles down the road this way. I'm saying miles because I've been in the US since 2003. Anyway, super excited to be here. So I'm going to be talking about a project that has been I've been working on for the last couple of decades. So I'm going to give you sort of big, broad brush strokes of the work that we've been doing, but really it encompasses work that we've been doing in high school biology through a complex systems approach. And I think Dr. Borelli did a great job. Oops. Let's see. All right. Anyway, before we get into the curricular activities, I'd like to share a little bit about the history of this project. It's been, oops. Oh, okay. Oh no. So my notes have, yeah, now it's showing the notes.
Oh dear.
Yeah.
I clicked small space box there.
Okay.
Always tech issues.
Yeah.
There we go.
Okay.
All right.
Anyway.
Should be good now.
Okay, it's been an ongoing collaboration with my colleague at MIT, where I did my postdoc with, his name is Eric Klopfer, since 2003. We started an adventures in modeling grant called, with this agent-based modeling tool, Star Logo. In fact, Star Logo and NetLogo started at the same time. And there's a little bit of a history which I will fill you in on. Anyway, that was a project that we worked on from 2003 to 2006, and then we had another grant funded by the National Science Foundation from 2010 to 2017. And that was to build curricular approaches for and particular biology units for high school biology integration. And after that, we've been examining how to scale the curriculum by capitalizing on MOOC technologies. And the next set of studies was building online teacher professional development for complex systems learning. And the most recent work with Clark Chin at Rutgers has been to revise the biograph curricula to support deeper and more accurate epistemic practices of modeling. All right, and for this presentation, I'm really going to be focused on this particular one from 2010 to 2017. A little bit about the theoretical and practical motivations. There are at least 4 influences on our work. The first has to do with the real world scientists and their understanding of the importance of complex systems. So this was called Keck Futures. I don't know if anybody's read about this particular one, but it was the National Academies of Science brought scientists from all over the country to all over the US to look at what are the biggest issues that are pressing the biosphere right now. They were multidisciplinary, and so they looked at things like the biosphere sustainability, disaster relief networks, the spread of disease. And the goal of this work was to identify optimal states and weaknesses within systems so that they could be fortified when perturbations happen. Second influence comes from the ambitious reforms in K-12 science education in the United States that was set out by the Next Generation Science Standards. And among those, the emphasis on STEM integration in the real world and how science connects to socio-scientific issues like ones articulated by the National Academies report. Third influence has been the long-standing issue of school science incoherence. And our interest has particularly, again, been in high school biology. Research shows that students just aren't able to develop a coherent understanding because standard biology curricula lacks coherent integration. And this in particular obscures dynamic and interconnected nature of phenomenon. For example, that ecological systems undergo evolutionary processes is something that actually obviously happens, but typically ecology and evolution are taught separately in high school. A fourth influence considers what disciplinary learning entails, and Susan Goldman and her colleagues at the University of Illinois, Chicago describe a really useful set of components that include epistemology, which asks what counts as knowledge of the discipline, concepts and disciplines and theories that bound the discipline, the inquiry and reasoning practices that are ways in which the first two components are established, the types of representational forms that carry meaning and are able to be interpreted by members of the discipline, such as graphs, equations, and symbols. And finally, the discourse and language structures, which are the lexical and argumentative norms of the field. For example, that science knowledge is built through peer review and consensus. And the next few slides, I'm going to be using this particular framework to describe how it is that we created our curriculum for high school biology. All right, so to start with, the first component, there are several ways that science educators have characterized systems. So some of you may have heard about the structure, behavior, and function framework, or dynamic systems, or system theory. If you're interested, I've written a whole lot about the differences between how we think about complex systems ideas. So anyway, we take an emergence approach too. So this is the belief that individual agents follow simple rules and their interactions create emergent aggregate level patterns that are observed over time. So to take the COVID example as illustration of emergence, individual decisions on mitigation factors like masking or vaccinations will dictate higher level patterns of disease spread, and the extent to which the disease is spread or contained is dependent on probabilities that a certain percentage of the population will follow particular rules. And of course, some level of randomness, such as mutations and of the virus that can change the course of the disease. So we built these models to allow students to observe these characteristics in 5 units that take 3 to 4 days of instruction to complete in the topics of ecology, evolution, gene regulation, enzymes, and sugar transport. The second component has to do with the core principles and concepts under investigation. And a key hypothesis here is that the field of biology can be understood and connected through complex systems, processes. And the ones that we are in particular focused on are predictability, so that systems outcomes often depend on initial conditions and that systems are subject to random variables. System dynamics, that systems undergo periods of equilibrium and disequilibrium, and that systems are subject, that there is continual and recurring change over time. The third one is order, and this is about the distributed and connected nature of system variables, and that this order is normally decentralized and nonlinear. And the last one is emergence and scale. This is the notion that complex patterns emerge from simple lower level interdependent interactions where complexity manifest properties that exceed the sum traits of individual parts. In the third component of inquiry processes, we've created a set of activity packs that ask students to work in teams to collect data and discuss how the data represents evidence to support the claims that they about the phenomenon. They also run different experiments to test hypotheses and predictions about the system. For example, whether starting with an initial number of variables will yield the same results in multiple runs. The fourth component is representational forms, and we use three kinds of representations to support sense making. The first one is the qualitative simulation itself that can provide an agent level view or a more macro level bird's eye view of the system. We also include mathematical representations in the form of graphs and variable frequencies that give quantitative measures of variables and how they change over time. And the last is a computational code that shows how the simulation has been programmed. So students can actually go behind the code and manipulate the code if they want, make some hypotheses around that. So students triangulate between all three of these representations to check to see whether their conclusions are correct. And the last component is discourse structures. And here students engage in collaborative discussions with scientific argument processes to come to consensus on a specific claim with accompanying evidence and reasoning. All right, so we're going to watch a short clip of that shows some of this work in action, and this is narrated by a teacher who's been working with us for over a decade, and he's been a design partner with us as well as a peer facilitator in our professional development. So we will play this.
When I first started participating in the Biograph project, I was really interested in finding a way to integrate technology into a biology class. I was very, very interested in finding a way to teach those modules to students in a way that used technology, used modeling, and gave results. I felt like I understood biology a little better after going through the module. I thought that was really important. You never get to see inside of the test tube looking at enzymes, but with a computer simulation, you get to see the individual components. That was another piece that I thought was really important. When we go to a computer simulation and you click the start button, you don't know what's behind the model. And with the Biograph models, you can see the code that develops the model. You can change the code, and then eventually, if you really enjoy making models, you can create your own model. I'm really excited about seeing teachers engage in using technology in a classroom. Are you going to use it to show YouTube videos or video simulations? Or would you like your teachers to use technology that generates knowledge?
Okay, so in the next few slides, I'm going to talk about how we assess student learning. We administered a number of assessments. I'm only going to focus on the biology content knowledge, the complex systems understanding, and also their understanding of biology as a coherent subject. And to measure biology content knowledge, we administered a 14-point multiple choice assessment where we actually took some standardized test items from different tests from around the country, like the New York Regents. To measure growth in complex systems understanding, we administered this open-ended question. Imagine a flock of geese arriving in a nearby park where geese haven't lived before. Describe how the addition of these geese to the park affects the ecosystem over time. This was also administered pre to post and scored on the 4 categories of complex systems understanding that I previously described. And to measure whether student participation helped them understand biology in a more coherent way, we held year-end focus group interviews where we asked these three questions. What do you think biology is all about? Was there anything in the Biograph units that were in common? And how do complex systems fit into biology? All right, and across 4 studies, we saw significant growth in both their biology and complex systems content understanding with fairly sizable student populations. The first column of the tables denote whether the PD for teachers was delivered in the face-to-face versus the online model mode. You can see that 2.1 was the pilot year where we were porting all of the in-person PD resources online. So we worked with a smaller number of teachers. I also want to draw your attention to 1.1 and 1.2. You can see that, I don't know if I have a little button here. No, I'm gonna try it. Anyway, but you can see that their effect sizes are slightly different, right? For biology content and also complex systems. And that the second year, the effect size went up quite a bit. And that's because it was the same teacher teaching the first and second year. So in the first year, they were the first adopters and they just got better at it and they were able to teach it a little better. Anyway, we've written a number of papers about the student learning outcomes and what we learned about the teacher professional development. Basically, what we found is that 2 years of PD is actually really important for teachers. Next, I'd like to talk about growth in their understanding of biology as a coherent field. And here you see a typical student's response in the focus group interviews. So this student says, I feel like complex systems govern kind of the overarching patterns that we see from stuff that's really, really tiny, like the organelles in your cell, like ribosomes and enzymes functioning to, and each of those cells go by another and form organs. Each of those organs form complex systems to form your body. Each individual body forms complex systems within a population, and it just builds and builds and builds. So here we see learning in several complex systems dimensions, including micro to macro level emergence, the interdependence of and the nested nature of systems, and how human biology and populations are connected through size and scale. Here's a second one. This student says, this is a little bit stochastic, the way that I mean, not stochastic, but staccato. This is, okay. All right, so I'm going to try to read it. I mean, all of the units just had like, it wasn't just sun hits plant and plant goes yay. It was like the protein goes over here, then the RNA reacts like this, then this hooks onto the here, but it hits here, then it does this. If it goes over there, then it does that. There are multiple factors all running around, doing their own things, and depending on how they interacted, when they bumped into each other mostly, the next step would look different. They were all like that. So here the student exhibits an understanding of how order in systems is decentralized, how interactions are nonlinear in these decentralized structures of systems, and that random processes fuel system dynamics. So I think those are pretty decent learning outcomes that we found over the course of about 5 or 6 years of research. Next, I want to briefly mention Biograph 2.0. This is the online PD mode where we investigated how to build a high quality PD for anywhere, anytime access. And I'm really not going to spend a lot of time on this, but I just wanted to say that we've seen growth in our teacher networks through our MOOC PD. You can see on the left side the number of teachers and how many countries we've reached in 3 years of implementation. The project has also spawned a number of different research studies, including how to improve online facilitation. We've also been interested in how to foster greater participation in our networks through informal social media applications like WhatsApp, Facebook, and Moodle. All right, the last thing I'll talk about is the next phase of this research that we're currently in. It's called DETECT. This is a mouthful. This is called Developing Teachers' Epistemic Cognition and Teaching Practices for Supporting Students' Epistemic Practices of Scientific Systems. Okay, so despite the growth we saw in student learning outcomes, there were some really suboptimal ways that we actually noticed students working with the models. And in a moment, I'm going to play the short video clip that really highlights what it is that we're trying to not rail against, but improve, let's say, in classrooms. So just to set up this clip, here there's 2 students looking at this particular simulation, and this is our sugar transport simulation. And they're asked to predict how many sugar molecules they expect will be formed when starting out with an initial amount of starch in the system, and then when an enzyme is added. And so let's watch to see what they do.
If you started with 60 start molecules, how many sugar molecules do you expect to form? You have to make a prediction, simulation, correct? Group prediction, I'm gonna say about like 50, 55. I have to run it. Ready? You ready, Lucia?
Why does it say hashtag, oh wait, this is number of sugar molecules?
It only produces 30.
That's fake.
Do it again.
Yeah. Yeah, that's so fake.
55. Right. We're starting with, we're doing it one more time.
But it was the same number of times, obviously, we didn't see.
No, see, no, look at this time. It's 49. Right. We do it again.
No, it's 49, fine. Brand, the simulation result was 49.
So inaccurate.
It's called randomizer.
All right, so you could probably predict what I'm about to say here, but some interpretation of what's going on. So they believe that the number should have been 55, right? And so one student saying this is fake, another one is like, let's keep playing this simulation to see if we can get that number. What's interesting is that they really never abandoned their initial idea about what they thought the number would be. They also didn't use the standard scientific epistemic practices, which in this case would be to take, multiple runs and average those runs, right? So we wanted to find out what other students thought about what the girls were doing in this particular video. And we decided to run a series of focus group interviews with students. And we asked them what they thought about this clip. So here's what one student said. I think that it shows the trust they have in prediction. Hold on a second. The trust that they have in their predictions and their hypothesis. It's kind of a good thing how much they trusted, but it's not that good because it took a long time for them to actually realize, oh, we're not going to get this kind of data. I'd say trust in the simulation is also as warranted as trust in your prediction. So this student's response is a little bit better, let's say, than the first two, but in the end, he's saying something akin to, despite what the data shows, it's good to trust your instincts. So, and probably many of all of you have read some of these books. There's a number of these recently published books on the issue of confirmation bias and science denialism and mis and disinformation. We're right now in the midst of working with biograph teachers to in this new project, in fact, to augment our curriculum to include epistemic practices to avoid this kind of bias and how this can be connected to real world scientific issues. So very briefly, last spring, we built a virus epidemic model. This has all the affordances of the other biograph models. In the top square, students can manipulate 5 different mitigation strategies that include hand washing and vaccines, lockdown, masking. They also can decide to set what portion of the population will comply with those strategies. In the circle, you can see the agents interacting with each other, and they all have a status bar over their head as they're interacting, right? Just which mitigation factors are actually working with them. The yellow color means that the person is uninfected. The red means that it is infected. The blue is recovered, and the gray is deceased. So the task for students to determine is to determine which of these mitigation combinations and strategies to follow in order to contain the epidemic outbreak. There's an 8-lesson unit with the model where students learn about good and bad, not so good scientific practices. They learn about peer review and norms for sharing their investigations. They also learn about the importance of comparing multiple results and making sense of anomalous data. It's all nature of science stuff. And finally, they investigate how to evaluate the strength of explanations. The unit then culminates in a scientific conference where they will evaluate other groups' conclusions. And each of the lab teams make their presentation. Students are asked to mainly focus on the methods, the practices that each lab group used, and the extent to which their evidence fits the claim, or the claim fits the evidence. Let's put it that way. Yeah. So we have 14 returning biograph teachers, many of whom we worked with over 5 or 6 years. And we're just finishing up data collection to see how this fared in classrooms. All right, and that's all for me. Thank you very much.
We're going to move to Jyoti Sharma from the University of Delhi, and the title is Capacity Building Pathways or Sustainability Competencies in Teacher Education Program, Proposing a Developmental Framework.
Okay. Not able to get it on the screen.
So you're going to do that?
Yeah, it's that. So, good morning, everyone. I am teaching at Delhi University, and this particular work is based on the national education policy the country has introduced during the COVID time, August 2020. So this national education policy came into the country after a gap of 3 decades. So we had our earlier education policy in 1986, and then we have this current education policy. As you know, that India being the second or almost the first, the highest populous country, and we are working, we definitely need to achieve targets on sustainable development. So we are trying to bring in sustainable development goals into our school curricula. So before we bring it to the school curricula, it is important that we need to train the teachers. So teachers should be ready to build in those skills within themselves before they practice them into classrooms. So this particular presentation talks about how what teaching is all about, what education, what should be the education goals, and how teachers can bring in sustainable development goals into practices. So it is more a theoretical model we need to build up because we are trying to build a green curriculum. So it is a pre-work before we bring in the sustainable SDG practices in the curriculum. Fine. So okay. No. Shit. Okay. So
I think there's an issue.
Yeah, that's that. So, so when we talk about how humans interact with environment, so human relations with environment are extremely complex and dynamic. So environment, so it is a process of co-evolution between society and environment. These are the premises we work upon. And within this complex process of co-evolution, society dynamics influence the impact of evolution. So the pace of evolution here in the current case is not the same. So it is not at equilibrium. So now we can't say there is co-evolution. It is basically the human, because human pace of development is exponentially faster than the pace of the environment. And that's why we say that we have almost eaten up the environment, you know. So let's go back to the 1972, the Club of Rome report, The Limits of Growth, which shocked the world and which highlighted the current rate of economic development is sufficient to run the globe out of non-renewable resources before the year 2072. And it was the projection somewhere 50 years ago, and now we are in 2023. And probably the way we are still growing and eating up the environment, it's not 2072, I think it will be 2052. So it will further lead to a sudden and uncontrollable decline in both population and industrial capacity of societies. And it further suggested that individualistic and piecemeal approach would not be sufficient to solve the problem. So I've just taken up a few important milestones in the journey of sustainable development when we start realizing that we need to save the environment. So when the UN came into picture, so from 1992 to 2021. So these are some important landmark in this development when the UN conference in 1992 talked about environment and development in Rio de Janeiro agenda in 2021. And then we do have SDG Decade of Action Plan began in 2021. So what we need to be sustained? We need to sustain nature, which includes earth, biodiversity, and ecosystems. We need to sustain life support, which are ecosystem services, resources, and environment. And all the more, we need to sustain communities, which are cultures, groups, and places. So how are we going to do this? We need to develop people, we need to develop economy, and we need to develop society. So if you look at the journey, so these are 17 SDG goals, which we are trying to achieve by 2030. Okay, so if you look at the journey of sustainable development, initially it started with the idea of sustaining the environment, save the environment. But now we talk about there is a interlink between environment, economy, and society. So you cannot isolate environment from the society and economy. So it is basically an intersection of all the three. So sustainable development will work at 3 levels. So we need to work on environment, society, and economy. So when we talk about environment, we need to sustain natural resources uses, environmental management, and pollution prevention, both at multiple level, air, water, land, and waste. When we talk about economy, we need to generate profit, circular economy to survive the population, cost saving, economic growth, and just fair economic growth, not a skewed economic growth, and research and development to have equitable coexisting societies. When we talk about social goals, so definitely standard of living, we need to improve the standard of living for developing countries and developed countries. So we need to bridge that gap. We need to have quality education for all. We need to develop communities which work on the equitable principles, and then equal opportunity. So there has to be, it is not always equality, but we need to work on the principles of equity. But there are intersections between environment and society. So when we say social environmental issues or development, so environmental justice, natural resources, stewardship at local and global level. When we talk about intersection between environment and economy, then energy efficiency, subsidies, incentives for the use of natural resources, we need to develop policies at local level as well as at global level. So when we talk about intersection of economy and social forces, then business ethics, fair trade, and workers' rights for more inclusive and fair society. So these are environmental sustainability targets. So sustainability at forestry level, agriculture, construction, water management, efficient lighting, and renewable energy. When we talk about sustainable development at society level, so then we talk about freedom, equality, solidarity, tolerance, respect for nature, respect for humans, and shared responsibility. Shared responsibility is very important. Responsibility for managing worldwide economic and social development, as well as threats to international peace and security. So must be shared among the nations of the world and should be exercised multilaterally. So that means now sustainable development is not limited to saving the environment. It is more now saving the humanity. And when we talk about economical sustainability, so that definitely climate action, innovation, equality, equal opportunities for quality jobs, democracy, and solidarity standing with each other in the time of crisis. So what are the challenges in sustainable development goals? If we look at sustainable development cannot be achieved by passing laws, awareness campaigns, and strict governance rules. There cannot be a capsule package of knowledge and skills that can be applied to achieve a sustainable society. Sustainable development can be considered as an ethos or a behavioral practice learned by every citizen that guides their action, practices, and decisions. All the more, it requires firm beliefs and conviction about the desirability of a sustainable society. And here comes the role of education. So, education for sustainability. So let's go back, take a step back, and what are the aims of education? Aims of education: individual achievements. We need to develop in skills and knowledge to our to the next generation, so that they can live happily and contribute in the society. We need to be education aims for the progress of individuals. Education means team leadership. Education means inclusive society. Education means team building, and then education means innovation and saving the environment. And when we talk about what is learning, learning is basically, there is a spectrum of human learning. So from individual to the more global way of learning. Human learning includes more than just adjustment to the environment. It is much more than that. So human learning includes more than adjustment. So it means striving for meaningfulness, understanding the world better, building peaceful communities, and celebrating nature and its diversity. So if we go by the definition in literature, so definition of learning means a change in human disposition or capabilities that persist over a period of time and does not simply refer to the process of growth. I am not taking up all these definitions. All these are taken from the literature. So learning, if we look learning from a dual lens, so learning for individuality and at the same time learning at the normalcy. So when we compare the learning with respect to certain norms. So learning is a process, how we learn, and learning as an outcome, how we are going to apply that learning. Learning at individual level and learning at universal level. So what are some of the characteristics of learning? Learning is a process which is continuous and lifelong. Learning is the process which leads to mental growth of an individual. Learning generally involves some degree of permanence, and learning prepares individual to adjust, adapt with the environment. Learning has to be purposeful. Learning has to be an active process, and learning should take place individually, socially, formally, and informally. And learning is a social phenomenon. So when we talk about learning for sustainability, so we need to keep in mind learning by observation, learning by imitation, learning by experimenting, and learning by insights. All these practices, all these models of learning are important when we are talking about achieving sustainable, teaching sustainable competences in our learners in the classroom when we are dealing with young learners. So cycle of learning basically is you start with a new experience and then bringing an equilibrium with old experiences and the new experiences, development modifications of experiences. Then there should be a growth and increase in those experiences, creating new experiences, synthesizing the old and new experiences, and again bringing in the new experiences. So this cycle needs to be completed. So when we talk about learners, so there is a difference between learner and student. So we need to make our students learner rather than students. I'll not go into detail. So learner can learn without a teacher, but a student needs a teacher to learn. So we need to aim our students to be learners so that they become independent when they move out from the school system. And the ultimate goal of teaching is to make our students lifelong learners. So when we are talking about teachers framework, so we need to keep in mind that all teachers need to keep in mind that all students are capable of learning. So we need to believe in human abilities. All students are unique and diverse, so that diversity needs to be respected and celebrated in the class. Students differ in their learning abilities, styles, interest, attitude, and motivation. And students come with rich learning experience from their local environment that needs to be incorporated when we are dealing with them. Students want a stimulating, accepting, and emotionally safe learning environment. So here is the teaching. So when I'm talking the role of a teacher, so teacher needs to be, so there has to be a multi-level relation between a teacher and student. So teacher needs to be a pedagogue, a counselor, a guide, a facilitator, and mentor. And there is a triangulation between educating, learning, and teaching. So that triangulation needs to be completed when we want to achieve our teaching goals. Another important thing, teaching is not equivalent to learning. So these are not two simultaneous activities. So when I'm teaching, it is not sure that all my students are learning. So don't think that it is a simultaneous activity. So teaching, so we need to make, we need to take the onus that instead of saying I have taught my students, the onus should be I have made my students learn. So when I say I've taught my students, I have put the onus on the learner. But when I say I've made my students learn, the onus is on me that all my students have learned. So that shift, paradigm shift, is important when we talk about classroom dynamics. And this should be the pedagogic cycle we need to complete as a teachers, from knowing, designing, scaffolding, analyzing, and reflecting. These are some of the stages of teaching and learning. So reboot means that you bring in students' previous experience of learning into the classroom when we introduce a new concept, situate the new concept into the existing models of learning, diversify, expand, and then accelerate, depending on the learning, the learning preferences of the learner. These are some of the pedagogical innovation a teacher needs to bring in mind. So there has to be a balance between hands-on and minds-on. Multidisciplinary approach needs to be put in. ICT integration is important. We have seen how technology can bring classrooms to life, and skill-based learning is important. So there is something. So now let's quickly talk about what should be the education for sustainable development. And I've told it, adjective education. Why adjective education? Because we say education for sustainable development. So what does it mean? So I've taken the very basic definition given by UNESCO in 2017, which says ESD should be understood as an integral part of quality education and lifelong learning. All educational institutes ranging from preschool to tertiary education and including both non-formal and informal education should consider it their responsibility to address sustainable development and to foster the development of key cross-cutting competences related to sustainability. The development of these competences is an essential contribution to efforts to achieve sustainable development goals. ESD equip individuals not only with the knowledge to understand SDGs, but also with the competences to engage as informed citizens in promoting the transformation to a more sustainable society. So this is the basis of the curriculum, teacher competency curriculum. So the role of education in the context of ESD is socializing role, preparing new generation to become active actor in shaping and contributing in the economical and social development of the world around, an instrument to induce behavioral change in a socially desirable direction. Then the final is shift in curriculum in response to a desired social change or new societal challenges. So these are some of the essentials of ESD curriculum: need and purpose, readiness, interest, perception, attitude, and motivation. So the curriculum should be at these 4 levels. The context and learning environment is important. For example, the sustainable, the education, the curriculum goals for the students in Canada will be different for the curriculum goals for children in India, because the challenges are different and the intensity and scale of challenge is also different. And then there has to be a reinforcement. So these are some of the psychological factors. Intelligence should be a part of it: readiness, motivation, interest, self-concept, learning styles, emotions, and attitudes. These are the teaching competences which we need to inculcate in teachers. Okay, so learner-centered, action-oriented, problem-oriented, participatory, collaborative, and self-directed. And we need to prepare sustainable citizens. So sustainable citizens, an individual who understands the complex world, who is ready to deal with uncertainty and risk, who can handle societal and global challenges with confidence and resilience, acceptance for others, believe in coexistence, act for a positive change in the society and in the environment, and ready to collaborate at multiple levels. So teacher and teaching competencies. So these are the competences both at localized level and at global level. So we need more collaborations among the countries within knowledge about sustainability and related issues, pedagogical content knowledge, how they need to teach, and then pedagogical content knowledge, how pedagogy, what should be the pedagogy for EST, and beliefs and practices for sustainability. So teacher needs to be a role model herself to because students do learn through imitation also. Teacher needs to practice that at her end. So towards education for sustainability. So it has to be learning to know, learning to practice, learning to be, learning to live together, and finally learning to self-actualize, which should be the highest aim of education for sustainability. So this is the framework we can talk about. At first, we talk about knowledge, both at content level and pedagogy level, then systems thinking, which is important, working together, collaborating together in a complex network, ethics and values, which are the backbone for any curriculum, because we need to believe that we need a desired society which is sustainable. Then there has to be some action plans which are result oriented, and then reflection so that we can improvise. So it has to be a very dynamic framework, developmental framework. And I'll just end with a quote that sustainable development, if we look together, it's holding our word in trust for our children. And that's why we need to work for this. And thank you very much.